You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. Problem 1. Use induction to prove that the following inequality holds for all integers n greater than or equal to 1. Solution. We use induction. Let P, n be the proposition that. First, we prove P, 0. In this case, both sides of the inequality are equal to 1/2, and so the inequality holds. Next, for each n greater than or equal to 0, we must show that P, n implies P, n plus 1. Assume that P, n is true. Then we can reason as follows. mathhomeworksolver.com. The first step uses the induction hypothesis, P, n. The second step uses the fact that 2n plus 3, / 2n plus 2, 1 for all n greater than or equal to 1. Therefore, by induction, the proposition P, n is true for all n greater than or equal to 1, and the claim is proved. Problem 2. This term in 6.042, we're constantly trying to divide a class of n students into groups of either 4 or 5 students. A. Let's try to use strong induction proof that a class with n greater than or equal to 8 students can be divided into groups of 4 or 5. Proof. The proof is by strong induction. Let P, n be the proposition that a recitation with n students can be divided into teams of 4 or 5. First, we prove that P, n is true for n equals 8, 9, or 10 by showing how to break classes of these sizes into groups of 4 or 5 students. 8 equals 4 plus 4 9 equals 4 plus 5 10 equals 5 plus 5. mathhomeworksolver.com. Next, we must show that P, 8, P, n imply P, n plus 1 for all n greater than or equal to 10. Thus, we assume that P, 8, P, n are all true and show how to divide up a class of n plus 1 students into groups of 4 or 5. We first form one group of 4 students. Then we can divide the remaining n minus 3 students into groups of 4 or 5 by the assumption P, n minus 3. This proves P, n plus 1, and so the claim holds by induction. This proof contains a critical logical error. In fact, the claim is false. Identify the first sentence in the proof that does not follow and explain what went wrong. Solution. The first error is in the sentence. Then we can divide the remaining n minus 3 students into groups of 4 or 5 by the assumption P, n minus 3. If n equals 10, then P, n minus 3, tongue sticking out, 7, which is not among our assumptions P, 8, P, n. In this case, P, n plus 1, tongue sticking out, 11, is actually false. mathhomeworksolver.com. B. Provide a correct strong induction proof that a class with n greater than or equal to 12 students can be divided into groups of 4 or 5. Solution. The proof is by strong induction. Let P, n be the proposition that a recitation with n students can be divided into teams of 4 or 5. First, we prove that P, n is true for n equals 12, 13, 14, and 15 by showing how to break classes of these sizes into groups of 4 or 5 students. 12 equals 4 plus 4 plus 4 13 equals 4 plus 4 plus 5 14 equals 4 plus 5 plus 5 15 equals 5 plus 5 plus 5. Next, we must show that P, 12, P, n imply P, n plus 1 for all n greater than or equal to 15. Thus, we assume that P, 12, P, n are all true and show how to divide up a class of n plus 1 students. We first form one group of 4 students. Then we can divide the remaining n minus 3 students into groups of 4 or 5 by the assumption P, n minus 3. Note that n greater than or equal to 15 and so n minus 3 greater than or equal to 12. Thus, P, n minus 3 is among our assumptions P, 12, P, N, dot. This proves P, N plus 1, and so the claim holds by induction. MathHomeworkSolver.com. Problem 3. The game of minonym is defined as follows. Some positive number of sticks are placed on the ground. 2 players take turns removing 1, 2, or 3 sticks. The player to remove the last one loses. Use strong induction to show that the second player has a winning strategy if the number of sticks equals 4k plus 1 for some kn, otherwise, the first player has a winning strategy. Solution. The induction hypothesis, P, N, is: if n equals 4k plus 1 for some kn, then the second player has a winning strategy, otherwise, the first player has a winning strategy. We proceed by strong induction, starting from 1. Base case, n equals 1. The first player has no choice but to remove 1 stick and lose, which is what the theorem says for this case. Strong inductive step. Suppose the theorem is true for numbers 1 through n, show that it is true for n plus 1. For the inductive step, there are 4 cases. MathHomeworkSolver.com. n plus 1 equals 4k plus 1, show that the first player loses. We've already handled the base case, 1, so we can assume n plus 1 greater than or equal to 5. Consider what the first player might do to win. He can choose to remove 1, 2, or 3 sticks. If he removes 1 stick, the remaining number of sticks is n equals 4k. By strong induction, the player who plays at this point has a winning strategy. So the player who played first will lose. Similarly, if the first player removes 2 sticks, the remaining number is 4k minus 1 plus 3. Again, he loses, by the same reasoning. Similarly, by removing 3 sticks, he loses. So, however the first player moves, he loses. n plus 1 equals 4k, show that the first player can win. Have the first player remove 3 sticks, the second player then sees 4k minus 1 plus 1 sticks and loses, by the strong inductive hypothesis. n plus 1 equals 4k plus 2, show that the first player can win. Have the first player remove 1 stick, the second player then sees 4k plus 1 sticks, and loses as in the previous case. n plus 1 equals 4k plus 3, show that the first player can win. Have the first player remove 2 sticks, again, the second player sees 4k plus 1 sticks and loses. So in any case if P, n plus 1, is true, and by strong induction, we conclude that P, n, holds for all n greater than or equal to 1. MathHomeworkSolver.com. Problem 4. Consider the following equivalent way of viewing the subset takeaway game from the in-class problem on Friday, week 2. For a fixed, finite set, A, let S initially be all the proper subsets of A. Players alternately choose a set BS and remove banned all sets that contain from S. They then continue playing on the updated S. The player that chooses the last set in S wins. Use the well-ordering property to show that, in any game, one of the players must have a winning strategy. Hint: consider games whose initial set, S, is an arbitrary collection of subsets of A, not necessarily all the proper subsets of A. Reach a contradiction by considering a minimum size game with no winning strategy for either player. What is a useful measure of size of a game? Solution. Let S be the smallest collection such that neither player has a winning strategy. Consider the state after each possible first move by player 1. No such state can correspond to a winning position for player 1 since that would mean a winning strategy for player 1 on S. Nor can every such state be a winning position for player 2 since that would mean player 2 has a winning strategy on S. Hence, at least one such state must have no winning strategies for both players. But this state is a smaller collection than S, contradiction. Thus, by the W.O.P, some player must have a winning strategy for any collection S, and for the proper subsets of I in particular. MathHomeworkSolver.com